Hello everyone and welcome back. Today we will be talking about the dew point and vapor pressure of gas mixtures or gaseous mixture. We will be um, first talking about the dew point. So the dew point is the temperature at which the air needs to be cooled to become saturated with water vapor. And it is illustrated by the following formula. We say that um, a gaseous mixture starts to condense and satisfying the following equation, wherein the sum of xi, or the sum of your components in the liquid phase, must be equal to 1. And sum of xi is also equal to the sum of yi over ki. And this is best described by an example. So let's say we want to condense or we want to find the dew point of the following gaseous mixture. We actually have the same mole fraction as in the previous problem. So 35% N-hexane, 30% N-heptane, 25% N-octane, and 10% N-amine. The same at total atmospheric pressure. So we can actually open the previous Excel sheet, and since the given mole fractions are in the vapor phase, we might want to um, replace this sum of yi with the given values. And since we know that it is already equal to 1, we can delete this one. And what we are interested in is to satisfy the condition wherein the sum of the hydrocarbon mixture, the mole fraction of the hydrocarbon mixtures in the liquid phase should be equal to 1. So we should set all of this. So we type the command sum and select all of them and press enter. Okay. So we need to establish an equation for xi. So we know that the xi is equal to yi over ki. So we need to enter yi divided by the ki. Then we can drag this down. And yeah. So initially we don't know the dew point, so we can delete that cell. Then go ahead to data, solver. So our objective is to have the sum of your mole fraction, the liquid phase, to be equal to a value of 1 by changing the variable cell, which is still in the same cell, which is B14. Then we press enter, and then once we click solve, it will actually solve for the dew point. So what you will be getting is a dew point temperature for the given mixture, which is approximately around 126.20 degrees Celsius. So it's just pretty simple. You can actually do the same calculation using the GOSIC command. So we can set this cell to a value of 1 by changing the cell. And once we click OK, it will have the same answer as well. Okay, so welcome back, and today we will try to solve the same problem using DWSim. So let's go ahead and click on create new with wizard, and we will try to input the information that we have in the problem. So we have annexing. Okay, so let me check. Then heptane, octane, and then okay. So let's double check hexane, heptane, octane, and amine. Click on next, and we will choose Bang Robinson property package. Then let's check the units. So I want the units in temperature, degree Celsius, and the pressure in atmospheres. So The rest we can just stick with the SI standard SI unit. So click on finish. We add a material string again, and then we want to go to input data and compound amounts. So we know that hexane has a mole fraction of 0.25, 0.3, and 0.3, 2.25, 0.1. So once you are done entering the mole fractions, click on accept changes and go back to string conditions. And we know that the flash spec should be the pressure and vapor fraction. And we know for a fact that the total pressure of the system should be equal to 1.5 atmospheres. Okay, so after setting the pressure at 1.5 atm, since we have a saturated vapor that is about to condense just before the condensation starts, we know for a fact that the vapor fraction or the vapor phase mole fractions is equal to 1. So that is about to condense, right? So we know now that the corresponding temperature, once you change to this value and press enter, you will approximately have 125.656, or and comparing it to the previous result, we have a dew point of 126. This is because we use a model for for our hydrocarbon mixture as an Antoine equation. We have that model. Whereas in this process simulator, we have modeled it using Baron Robinson, which is more accurate in my opinion. And when you try to check it using the HYSYS and using the Antoine property package again, you will also have this dew point temperature nearer to what we have calculated using the Excel sheet. Okay, so going back to the vapor pressure determination, so we are asked to find the vapor pressure of the three components. So we need to find the vapor pressure of N-hexane, N-heptane, and N-octane, and N-onane at 130 degrees Celsius. So we need to find the individual vapor pressure of these components. This is relatively easy since we already have established the Antoine equation in our Excel sheet. We just need to change the temperature to 130 here, and the corresponding changes will occur. So since these are all in atmospheres, we know that the vapor pressure of N-hexane at 130 degrees Celsius is around 4.9 atmospheres, N-heptane is 2.32, N-octane is 1.13, and N-onane is around 0.56 atmospheres. So that's just basically it. So we don't actually need to care about the sum of these X components or the mole fraction of each component in the liquid phase, since we are only interested in determining the pure vapor pressure of each component. So we will just into this column. So that's it. That's very easy, and I hope you understand the topic. Okay, so going back to our flow sheet, we will try to determine the vapor pressure of each compounds using the DWSM. So we can go to the input data, then compound amounts. If we are interested in determining the vapor pressure of the N-hexane, of pure N-hexane, we set this mole fraction equal to 1 and setting the rest of the components to 0, and then click on accept changes. And then we set the flash spec to temperature and vapor fraction. Since we want to get the vapor pressure at a temperature of 130 degrees Celsius, we change this one. And the vapor phase mole fraction should be equal to 1. And as you can see, we have a a pressure corresponding to 4.96 atmospheres. And this is the corresponding vapor pressure of the N-hexane. And we can actually do the same for N-heptane. We just need to zero out those components that we are not interested in and setting the N-heptane again to 1 and getting the the accepting the changes, I mean, and then going back to the stream conditions, applying the same temperature and the same vapor phase refraction. We have 2.33, comparing it again to our spreadsheet calculation. So we have a fairly good approximation using the endpoint equation. And let's go once again, setting the N octane to 1, accept changes, going back. So we have a 1.12. Okay, again, very good approximation. 0 and 1. Accept changes, going back to stream conditions, we have 0.56, and again, it's approximately the same.